angry and at his wife. And he has his two children, two sons. So he tells both the sons, ask the first son, go kill your mother because she's been bad. Okay. And so the first guy says, of course I'm not going to kill my mother. So he gets mad at this guy and he kills him. Okay. And so he asks the second guy, go kill your mother. He says, okay, he kills his mother. And then, he's very happy with his son. So he asks him, what do you want as back, as a reward. He says, I want my mother back. Okay, and so he gets his mother back. I'm reminded of this story because if you're late for turning in your project, if you come to the class on time and ask me, can I submit it at the end of the class, that would be great. This is actually meant for the people who are watching this on the video. But if you miss the class, in essence, then that's not necessarily a smart idea. Because then you're not going to be able to ask me for extensions. Okay. Anyway, so I guess presumably half of the class is still doing this project. So we will assume that those are all late submissions. And then what I'm going to do today is continue a little bit of discussion of hidden Markov models that we were in the middle of basically completing last time. And then start talking about information integration. Before I start, are there questions? Yes?
Are you going to provide like a practice final exam? / last homework assignment?
I will let you know. Okay, I mean, you will know about it. I haven't made my mind on that.
Okay. The homework assignment that you said you might.
That's what I'm saying. So, you will hear about that soon.
Okay.
That's a good question. Other questions? Oh, by the way, so the TA said that he's going to send a mail soon with instructions on how to sign up, essentially. These are the sign-up sheets. I think you just do it online, essentially. So, and it's be like a 10-minute slots for each of you, starting Monday afternoon, every afternoon, Monday, Tuesday, Wednesday, Thursday. Okay. So that's the thing.
And then be on the course website?
He will send you an email. He's setting it up on some Moodle or some place, where you can just online, sign up. Okay. Any other questions? Okay. So we were talking about the learning phase. So there were three main problems in HMM, right? Let's see. The three main problems are figuring out, given a sequence, how likely is that sequence, and the second is given a sequence, what is the most likely state that could have caused that sequence. So in some sense here, in one case you are computing a simple joint probability. Remember that. So the way to think about HMMs is you're going from states, and each of these states are outputting observations. Okay, and so when I talk about a sequence, all you get to see is this observational sequence. Okay, the first question, observational likelihood, is saying if you were to see a particular sequence, then what is its probability? So you're asking the joint probability of word 1, word 2, word 3, etc., word k. And as I mentioned, as we talked about last time, these words could have been produced by different state sequences, because a particular word W1 could have been produced either by S1 or S2 or S3. It's possible. Okay? And so because of which the naive way, that's why I said the naive way to compute the observation likelihood would involve essentially considering all possible state sequences, and then for each of those state sequences compute the probability that they will generate this sequence, and then add up those probabilities anytime this sequence is generated. So this is a joint probability query. Okay. This one, on the other hand, most likely state sequence, which is decoding, which is actually the most useful thing for you in information extraction, where given these observation sequence, what is the most likely state sequence that led to this observation sequence? Okay, so it's a probability, but for doing that, you need to do probability of S1, etc., Sk, given O1, etc., OK. And then you're trying to find the max, the state sequence which has the maximum of that probability. Do you get that? So it's a conditional probability that you're trying to compute here. And in general, conditional probabilities, PA given B is A and B. Okay. And as I said, remember that the most useful thing you want to do with information extraction with HMMs is this problem, decoding problem, because you're trying to provide labels to all the hidden states at the same time. Okay. Now, keep in mind also that basically would involve computing this conditional probability. Okay. However, one of the things we'll see a little later is that actually the HMM, hidden Markov model, if all you wanted to do is just this, then hidden Markov model turns out to be more than you really need. Because hidden Markov model not only will, it essentially generates the entire language, because it generates the states as well as the observation sequences. Okay? In particular, from probabilistic theoretic terms, this is a model joint probability of the S1 to Sn, O1 to On. It's a joint probability distribution of all of it. But really, if you're only going to be asking this question, then you are better off thinking only of that distribution, S1 to Sn given O1 to On. Okay? The reason I bring this up is, as useful as hidden Markov models are, there is this other model. Actually, since we're talking about this, we'll go there. This one. So the other model called conditional random fields, which essentially try to only model the conditional distribution directly. Okay, and so in some sense, this, and it's been said that conditional random fields actually are more useful if all you want to do is just figuring out the most likely state sequence. Okay, because remember that essentially if all you wanted was PA given B, okay, now if I actually am modeling PA and B, PA and B is actually PA given B times PB. Right? Okay? What that essentially means is that the full joint distribution is also capturing the distribution. So if you're for us, basically, you're thinking in terms of stuff A and B, that's right. S and A. State given observation, that's what you want, right? So you are essentially talking in terms of state and observation is state given observation times observation. Okay, so you are actually modeling more than is needed if all you wanted to do is just compute the distribution of state given observation. And that's the point that's being made here, that HMMs are actually generative models and they can be used for this task, but sometimes they're more than is needed. Okay. The other thing I wanted to mention with respect to this discussion is, we were talking about the learning part, and in the case, again, this is something repeating from last time, which went probably too fast. If you're talking about HMM learning, if you have completely tagged data. That means you have essentially, if you're thinking of part of speech tagging, okay, then if I not only gave you the sentences, but I also showed you which words are which parts of speech, which words correspond to which parts of speech. If you do that, then I have a lot of training data. Not only do I have training data, I also know the classes of each of the words. And using that, it is quite easy to essentially learn the probability parameters for HMM. Okay, and that's what we were saying last time. And we can go slower this time. So if to get the state transition probabilities, that means if you are in one state, what's the probability that you'll go to another state? That's one type of probability. The other type of probability is the observational probability. If you are in a state, what's the probability that you will get a particular observation? Those are the two things. Okay. It turns out that if I just have this information, then I can compute both of them as direct ratios. Okay. So in this particular case, you are looking for so if I'm trying to find out what's the transition probability, that if you are an I, you will go to J. Okay. So you will go through all these sentences looking for, so remember I to J, let's say I'm trying to find noun to proper noun, determinant to noun, okay? So whenever I go from pink to green, from red to green, that's an example. Every time I go from red to green here, that's an example, or one example, two examples. Okay, so the 2 would be in the numerator. Okay, the denominator is how often do I actually have reds? Okay, 1, 2, 3. So there were 3 times, no, and 4. There were 4 times I had this class, and then of them 2 times I'm actually going from that class to this class. So the number of times I transition, the fraction of times I'm transitioning from SI to SJ is being computed here. Okay? The other one is again, if you are in a particular state, what is the probability that you will give a particular observation out? Okay? So for that, in essence, what you're looking for is how likely is it that the word the would be output when you are in the class state? How likely is it the word dog would be output when you're in the class now? Okay. Now the interesting thing here is that obviously the is never being output in the noun class. So you would get a 0 for that probability, and you will get, and the dog is being output at least once, like 1, 2, 3, 4 greens, of which one time dog was output. Okay, so 1/4 would be the observation probability of dog when you are in the noun class. This is what you're going to be computing. The one thing that, so that's all this is saying. One thing you want to keep in mind is that whenever you're getting these probabilities, some of them are 0 probabilities. Okay, you need to worry about regularizing the ratios, because it's possible that you just have a small set of training examples within which you did not find, for example, according to this, what I would say is the probability that raw would be output when the class is noun is 0. Right? Now it turns out that actually that class raw would be output for any class is 0 right now, according to this data, because none of these, there is no word raw here. Okay, so if you jump to the conclusion, then you will put a 0 for that, that particular observation. Okay, and then once you have a 0, you're dead. Okay, so because of which, remember we talked about the regularization, the Laplacian smoothing. That's what we do here too. So you add a denominator and a numerator value, such that that particular part slowly wears off if there is enough training samples. Okay. Now the interesting thing is that comes in collision with the question of whether or not you really need the topology of the HMM upfront. one of the questions is, if if I'm anyway going to find out the observation probabilities and the transition probabilities myself, okay, then why do I need to tell you which states transition to which other states? Assume everything transition to everything else, and then if some of them are zeros, just remove those. Now the problem is you would not leave anything to be zero because you're regularizing. Okay, so some of the small probabilities essentially could be there because it's really an unlikely transition, but it still is possible, or because essentially you just smooth the transitions from the sample data. Okay, so the general assumption is, anyway, if I'm assuming all this, then I might also assume that they provided me both the HMM and, both the states and the transitions. So the topology of the entire network. Okay, so that's the assumption. Now, if the topology is not provided, if in fact I don't have training data which is already pre-labeled, then as I said, this is not going to work. Okay, then you need to do a much more complicated thing, which is sort of involves expectation maximization. That I'm not showing here. But that's also doable, it's just more costly. Okay, the idea in using hidden Markov models for information extraction tasks is partly you can decide to model parts. You are supposed to model the entire document, okay? But then you can say large parts of the documents correspond to the state, I don't care. Okay, and so if you are, for example, talking about title, then and you're most interested in picking up just the paper title, then you may be able to write a little HMM for just the title block, which still ignores a lot of information about addresses, for example. Okay, but then you need to say that, oh, this looks like the author name, this looks like the title part, and this is some rest of the part of the title. Okay, and so you can generate, you have this one HMM that's capturing the entire title, and then you train this, and then use this to figure out, what's the classification for the words in the title, and those words which actually correspond to author name class will be the authors. Okay, does it make sense at all?
So you said that we are just having HMM for title. So title can include what?
No, I'm talking about the title block. So that could include, for example, the paper title. And so this could be, let's say, last name, state, first name, state, and the paper title, like paper title class.
But no addresses.
Yeah, and so the rest I'm just ignoring it. If I didn't put it, then I ignored it. Okay? The point is that you have, and you can look at the same document with different HMMs and then catch up, remove pieces from it. You can have one HMM that captures the title, the names and names of the authors and the title of the paper. Another HMM that might capture the citation information. And notice that for citations, each citation is again an HMM. Because some people write the title of the paper first, then the authors, then the conference name, then the year, and sometimes before the conference name, after the conference name, but before the year, you might also write the location where the conference is held. Okay, so you will wind up having to write, remember that complex HMM, you have to write one of those. That's essentially, you're providing background knowledge as to how to look for constraints between different parts of the paper. The only advantage of using HMMs is at least the probabilities of transitions can be computed directly from the data. And having done that, then you can find, given a set sequence of words, you can find sequence of words that you think are for the citation, you can find which parts of these words correspond to the author name of the paper, which part of these words are most likely to be the title of the paper, and so on. Okay? And this has been used multiple applications, and actually this one just shows, this is probably old information right now, but this shows that if you're just trying to catch named entities, like for example authors, a list of authors from a set of PDF files on papers. Okay, then essentially the reason you are in this case, the reason you are modeling the organization is because authors come right before the organization. Okay, but then all you are really interested in is catching the author names and putting it somewhere. And this one is saying that you can get pretty high F measure, precision recall connection, like computer measure. In this case. Okay. And as I said, in general, this is like a bigger issue than just HMMs and this particular discussion. When you are modeling, when you are using a model, a probabilistic model, then either you can talk about generating probabilistic models, which generate the entire data. And so, as part of it, they can also answer any query. So if you ever model the joint distribution over a set of variables in probability, then you can answer any possible probabilistic query you ever want to ask on those variables. But if you're only ever going to ask queries of type P state given observation, then this might be sort of a breaking the egg with a sledgehammer. In a sense, you're doing more than is needed. Okay, so there is this whole interesting issue in learning literature, especially probabilistic models, whether generative models are good or discriminative models are good. I'm not going to get into it, but I just wanted to point out that the connection is, in one case, you are actually modeling the joint of POQ. In another case, you're only modeling PQ given O. Okay? That's basically what I'm going to say about the information extraction. And I'm going to transition to information integration, discussion of information integration, which is going to be sort of for just the rest of today's class mostly. Are there any questions on this?
So like the whole point of the HMM is to like pretty much given some page you can just go with per word and just figure out whether this is going to be an author or not. Just give some word on the page.
It's going to be a particular class. So you are hopefully, supposedly you're trying. So again, remember, information extraction is trying to fill a table, a relational table. Okay, it could be an n-array relation, it could be a binary relation, it can be a single array relation. And the question then is, you have the column names, okay, and you are given and basically given some information which has the values of C1, C3, C2, C4. You want to extract them and put them in this table. Okay. The example of the header page of that, the title block of a paper, you have the author name is one column, author's first name is one column, author's last name is another column, the title of the paper is another column, the address is another column. In the text itself, they may have been put in all possible ways with extraneous information coming in between. So you wrote an extractor, an HMM-based extractor that extracts the pieces. Once you extract the pieces, you put this in this table, now you have a database of this information. Okay? And for each one of these relations, you will have to write a separate HMM. That's the basic idea. Yeah?
Can you explain about the hidden thing?
The hidden part is that the state is hidden. You never are told that, when I give you the paper, I won't say the author name. So I won't say the title, and then write the title. And then author, and then write the author name. Okay? And so you don't know the class of the words. All you're interested in finding out. So for example, if this is the table that I want to fill in, okay? Suppose the papers were written in XML format, okay? Then do you need HMMs? No. Because XML is essentially already self-describing the data.
Unless it's lazy. Unless it just...
Yeah, if you put the whole thing in cat data, then you're sunk. But if it basically already said, author begin and then blah blah blah, author end, and then address begin blah blah, address end, then title begin blah blah, title end, then I can pick this part, put it in the other part, this part, title part, and put in the title and so on. Okay, but this information is hidden. So it's like you can say as crazy as it may sound, you can think of normal text as being produced by starting from an XML file, removing all the tags. Okay? And you're trying to recompute the tags. Or equivalently, in fact, it was produced from this table, perhaps. Both, whichever you like, whichever analogy you like. So there's an XML file with the tags, and the tags have been removed. You're trying to reconstruct the tags, and those are hidden. And you never see that because you're trying to compute what those would have been most likely. That's why it's such a. Any other question?
So this is the clarification. So we are generating a model. That's why it's called generative method, right?
So in this particular case, you will generate both, so you generate the states as well as, so there is a way of generating. So one of the interesting things is, if you believe that you have a pretty good HMM for titles, okay, this is a good question about HMM. So suppose you have some data, title blocks. You have provided, you have compressed that data into a generative model. So HMM is your generative model. If this is a generative model, then you can throw away that data. And any aggregate question you could have asked on that data can be probabilistically answered just on this model. Okay? So in essence, you can run, remember there was a slide earlier, you can run the HMM to generate a title block now. Okay, start and then go to the first state. Start can go to any of the states, go to one of the states with the right probability, pick an observation from there, and so on. And then you will generate a title. Okay, so if I can go back there, so statistically speaking, if you were to do that and generate a whole bunch of title blocks, they are similar to the title blocks you would have seen in Google Scholar. Statistically, they don't actually correspond to any real paper, but they correspond, the statistical properties of that generated data is the same as the original data. That's what you say. Again, this part of the discussion is in some sense clearly out of the scope. I just had some extra time today, plus nobody was there, so we should be talking about anything we wanted. So I thought that we should talk about this, but in some sense it's out of the scope of the discussion we are doing, because this is more about the, the foundations of probabilistic models and learning with probabilistic models. Okay. And the best I'm expecting you to understand here is that you can apply HMMs. Any other questions? Okay, so there are no questions, no other questions, right, on the other stuff. Okay, so what I'm going to talk for the rest of the class today is mostly to talk about kinds of tasks that get, so the issues of it, that you come across in information integration. Just as information extraction had a long overview of the kinds of issues that come in information extraction and a couple of examples. Okay, that's more or less what I get to do here too, because it's an area that is still in flux. So I'll tell you that there are lots and lots of different kinds of problems get considered as information integration problems. We'll talk about the dimensions of variation, and may probably not even talk about any specifics, because I'm not convinced enough that any very specific idea has a place in an undergraduate course like me. I know that most of you are graduate students, but this is an undergraduate course. Okay. So I will actually mostly get you to understand the dimensions of variation, and then might talk about maybe some examples. Okay, so in some sense you could say that information integration coming at the end of this course as the last topic is just the right thing, because in some sense that's what you've been trying to do from the beginning. Okay, so you have the web data, right, and then you can basically do keyword search, and which will give you pointers as to what pages to look at. And then on top of, and basically what you're doing is when you're extracting patterns from this data and then putting in some databases, for example, and then you are able to do database style querying. One of the interesting questions then is if an answer to a particular question depends on some information in this page being combined with some information in this page. So for example, I have a telephone number. Whose telephone number is it? And where do they live? Okay, there may be one page which says this is the telephone numbers page, and this is another page which says these are the people's addresses. And you're sort of, when you hear integration, think join from the databases. That's integration. So you're taking information from two different pages and combining them. The way information integration happens at the lowest level is in your head. Right? You essentially ask Google some keyword query. It'll show you a bunch of pointers to various pages. You read a bunch of them, and then you ask another different query. It'll show you another bunch of pages. You read another bunch of pages. As long as things slosh around in your head, you're able to then combine the information and answer more questions than each of the pages. What we are trying to do is can some of that at least be automated. Okay? And in particular, had you been, one idea you can already see is if you had actually extracted patterns from the textual data and filled up pages, filled up tables. Now you have a database, so and there could be different tables that different people have extracted, and you can combine these tables and do joins on them. If you remember the semantic web part, on top of these tables, there may also be background knowledge axioms, and so you can answer queries that actually are more than just the joins between databases. So, for example, in the Ramayana example, I might be able to ask things like, even if I only tell you that somebody is the wife of somebody, I might be able to tell you whether or not they're a spouse of somebody. Even if the table doesn't say so, the background knowledge tells me so. Okay? All of this is information integration. You're combining information from different places and answering queries. So that's what it's telling. There are bunches of example information integration tasks here. For example, if you're doing comparison shopping, there are bunches of sites which will try to pull data about the cost of a book from multiple stores and show you prices. That's an information integration task. This information is available in different places. Rather than asking you to go to all of them, each going to all of them and giving you the information. Okay. Then things like kayak, which is this, you give one single travel request and it just goes to a whole bunch of sites and presumably makes up these flights. Sometimes 1,500, 1,700 flights, nobody can actually go through all of them. But it's basically, it's integrating information. Okay. And then, so that's one type, that's in the open web. One of the interesting thing is that this integration of information can also happen, one of the tricky things that sort of subtle point to understand is when you think of web, and when you think of this course of web, when you think of IR, you tend to think mostly of web. Because you mostly thought of Google or some search engine. But IR was originally done on essentially text databases that are directly under somebody's control. Okay, so in general, most of these technologies, whether it's IR or information extraction or information integration, doesn't always have to be done on open web. It can also be done on your own 15 databases, so your personal databases, your personal information sources. If you remember, I talked to you about the NSF example where they have this information in their databases as to how much money they are giving to historically black universities. But to figure this out, they had to do integration in the hard way, which is, people have to look at all these databases and then write down on pieces of paper, collate them and say, okay, this must be the amount of information. Okay, so there you are integrating information across heterogeneous databases, heterogeneous data sources. Okay, and then you can also have intra-corporate. Basically, that's the same thing. You can have personal information sources, intra-corporate sources. Okay, so a corporation might be having a whole bunch of databases. They're not web pages; they're actually databases. It's just that different people came up with the schemas for different databases. Okay. Now, if just think about it. If I give you a piece of, a set of data, like the student data, I'll give you. Think of this as 412. Is 412 the database course? I think 412 is the database. Yeah. So think of this as 412. I came up with the student database information, student data source information, and gave it all to you and described in English what this information contains, and I'm asking you to make up schemas and store this information in your database. So essentially, I tell you that I'm giving you student data information, and for these people, I give you the first 15 pages of the information. This guy's next 15 pages, those guys next 15 pages, and so on. So this class now has 8 student databases. What do you think is the probability that you, all of you have, without talking to each other, come up with the same schema? Extremely low. Now if I say combine your databases, you're stuck. Do you see what I'm saying? So in general, this kind of a problem you assume will happen on the web anyway, because on the web nobody talks to anybody. Everybody is making up their pages, and they're not even writing it in a structured form. But the interesting part is, even if in fact you have started to write the data in a structured form, you may actually be able to write them in heterogeneous structured forms. And so some of the issues are the same. Making them work together is information integration. Okay, and from that point of view, science informatics is this whole area where people are interested in combining, let's say, integrating genomic data in multiple different databases and combining them and doing, query processing on top of that. Integrating geographic data, archaeological data, astrophysical data, etc. There's a whole bunch of interest in that. Now, this doesn't come across as Google or web, but this is just some of the issues are the same. And as I said, companies are interested in this sort of stuff too. And the stuff that you probably are aware of most is this, which is basically like kayak kind of scenarios. Okay, and so the examples, kayak, Expedia, here are DBpedia. I mentioned that DBpedia is the one that I think, the Infopedia, DBpedia, that's the one that was taking information from all the Wikipedia articles and putting it into a single database. Okay. Things like Libra, CiteSeer, they're also actually information integration systems. Right? So Libra, you may not know Libra, but so Google Scholar, I didn't mention Google Scholar here, but Google Scholar essentially is an information integration system because it's reading a whole bunch of papers, extracting information from them, and it can then answer aggregate queries on this, saying what is the most cited paper in an area? Who is the, what is the maximum number of citations to any paper written by this particular author? These are all, these queries couldn't have been answered on individual papers. You have to integrate the data from individual papers. It's an aggregate query. So those are also integration systems. Okay. So to some extent, this is what you had in mind when you were extracting information and putting into a database. Now notice that you can't do much of this at all if you are only doing keyword search and showing pointers to people. So information integration doesn't make sense in the search engine world where you're just pointing, you're providing pointers. So it's more of a question answering issue. Okay. The other thing that is worth remembering, so I said, there's this question of open web contains textual information, and you might want to capture the structure of them and then put them in structured data. You may also have structured or nearly structured heterogeneous databases in your own company or in your own personal desktop, and you may want to integrate them. Another reason is that, in fact, when web became the medium, as popular as it's become, now it has a whole bunch of databases that are accessible on the web. They just put an English front end. They put a form, they put an English front end, and then you fill the form, and then this query is actually executed on the database. And then they will give the answer out in some pseudo-English form. Right? We talked about this. This is the reason why, in fact, those kinds of, the pseudo-English documents, you can extract the tuples from them much more easily using wrapper generation techniques. But that is just to extract the tuples. But then you can actually also, take the tuples, taken from this source and join them with the tuples taken from this source, and that would be information integration. Okay. So in general, the point here is there are a large number of sources on the web, databases, which are actually databases. They're structured sources. They just don't tell you that they're structured sources. So most of them are really databases. Okay. Now what's interesting is that based on who you asked, the estimate is that this can be actually larger. The amount of data in the structured sources on the web can be larger than the textual pages that you see. Many pages are actually generated on demand from a structured database. Okay, so that basically has been called the deep web. So the web which is being dynamically generated with a database backend. Okay, and that is yet another reason why you are interested in information integration, because if there is this information, about information about countries and capitals, and another piece of information, another source which tells you city names and weather, then I should be able to tell, what is the likely weather in the capital of a certain country. Okay, right now you do it by, writing two different queries. In information integration, you're trying to do it together. Okay, in one query. Okay, so that's another motivation. Okay. So that's all about motivations, and I basically want you to think of this silly picture. You have, on the web, on web accessible, you have services, you have web pages, you have structured databases, you have sensors, you have all sorts of stuff available on the web. They all can be accessed using basically HTTP protocol and forms and whatever. Okay, and you have a computer, you can access the web. Right now, you are integrating the information in your head. The integration is occurring in your head. So you try to figure out, you send a query, you get pointers saying maybe this might have an answer, maybe this page might have an answer. You'll read the page, you'll figure out the answer, and then feed it into some other page mentally yourself. Okay, so the holy grail of information integration should be essentially what should come in the middle here, such that that middle, think of it as a mediator, a universal mediator that takes your queries and it basically knows how to outsource those queries onto these sources and combine the pieces of the information and answer it. That's one way of thinking about what information integration is. Okay, not pointers, but you take the query and directly figure out what sources would be relevant, send, pick the information from them, put them together, construct the answer, and give it back. Now, in saying this, I'm actually there's a whole slew of challenges as to how to make this happen, automatically make this happen, right? For example, the simplest thing, if you are writing a little mediator here, the thing that you can do is you take this guy's query and send like a broadcast message on the web. Stop whatever you're doing, answer this query, right? And basically, that means every source now has to look at this query and figure out whether or not it can answer it. That makes no sense, because the sources don't even know that you're trying to use them. Okay, so in some sense, the mediator which sits here has to figure out what are the relevant sources, how to pick the information from them. If the information from them comes in sort of unstructured format, extract the structured information from them, extract the structured information from them, and then join the information if needed, combine it with the background knowledge, answer questions. I mean, if you're dreaming, might as well dream big. That's the dream here. Okay. Now, what I want to, and so different people have come to this dream for different reasons. And in essence, I'll tell you at least three views. IR folks, when they talk about information integration, what they are talking about is, you mostly care about structured, unstructured data, from which you first compute the structured information, put it in a database that's under your table. Okay, remember information extraction gets the tuples, puts it in a table. And now you have a database, answer queries on it. Okay, the only question, of course, is now this database, as I mentioned, is likely to be not a clean, curated database. You may have extracted information that is erroneous. You may have extracted information with missing values of some of the attributes. You may have extracted inconsistent information. The whole entire tuple that you extracted may be actually iffy. Maybe it's only 0.9 true. That means your extraction algorithm may have missed how to extract it correctly. So the probability of existence of this tuple is only 0.9. If there's a tuple in a database, you assume its existence probability is 1.0, right? That's what normal databases say. But if you are extracting a tuple from text, it could just be 0.9 because your extractor may be, noisy. So if you come to information integration from that side, it's sort of you're thinking in terms of how to extract, how to model the probabilities of the extracted data, how to combine, how to do inference on probabilistic databases. That's one way, okay? I mean, I'm not saying that's not a problem, that's an important problem, okay? On the other side, you can actually be thinking of people who have, like the people who have multiple heterogeneous databases. So for example, multiple of you have come up with different schemas for the student data. Now I want for you to get along and answer questions, aggregate questions on the student data across all these databases. Furthermore, I could make this more interesting and say, this part of the class makes 8 student databases, and this part of the class makes 9 course databases. And you really want to be able to see, whether or you may want to be able to answer which pair of students are taking more than 2 courses together, for example. Okay, now you need to first of all, aggregate the information from all these databases. They're all sort of exporting the same sort of data. Okay, you aggregate the information from this set of databases, aggregate the information here to get all the information about courses, and join the information across. Okay, if you are thinking about that, then you sort of have a database view of information integration. So you sort of assume these guys are mostly interested in first figure out how to extract the information to structured form and mostly put it under the table. These guys are assuming that in some sense the information is already sort of structured, but just because it's structured doesn't mean they get along. Data may not be interoperable because they have completely different schemas. And furthermore, in general, something that we take for granted is not only can the schemas be wrong, but in fact, in certain scenarios, the same entity may have been written with slightly different spellings in different parts of the database. So that means even the tuples might actually be heterogeneous. So there are these 2 problems, that this particular part is up. One is the schema mapping, which is how to map schemas across databases, saying what column here corresponds to what column there. And then you also want to talk about if I give you 2 records, are these records talking about the same entity or not? Okay, and so that is, one is the value mapping, one is the attribute mapping. Okay. And those are the challenges that you start thinking about if you are here. If you are looking at information integration from the database side, then you will be thinking in terms of how do I map the schemas, and how do I do the record linkage, and how do I do query reformulation. So in particular, one of the interesting questions might be that you made these databases, they're not all fully relational. In particular, the databases that are accessible on the web, you don't get to ask every query on that database. And I mentioned this at some point of the time in the semester. Amazon has a database of books, right? They know exactly what they have. And I have a query. I'm into buying books which have, prime number of pages. Okay? And the total number of pages should not be more than 400, less than 300. Okay, it should be more than 4, so it's sort of between 300 and 400, and they should have a prime number of pages. That's all I care. I don't care about who wrote it, what language it is in. Give me those books. Okay? Amazon, unfortunately, doesn't have enough of my kind of customers. They don't allow me to search that directly. They can answer that question. They have a database. They can answer this question. Okay? So just because the database is accessible on the web doesn't mean that every query that could have been answered by the database manager can be answered by you. Because you provide a view into the database. This is again normal 412 idea. Every database, so in fact, the bank guys know how much money is in everybody's account, and the Blackboard system knows, the teacher who's accessing the Blackboard system knows which of the grades of all of the different students. But each student only gets to know their grades. Right? So you have a view. right? So the question then is, just because there is access restriction doesn't mean queries cannot be answered. I mentioned that there is in fact a way of figuring out, at least 3 or 4 books which satisfy me. That is, they have prime number of pages between 300 and 400. Just keep asking for books and look at the pages. And if the number of pages is a prime number, then return it. And if it is between 300 and 400. What did I do there? I took the original query, reformulated it into a set of queries that can actually be answered by the source. This is a pretty crazy reformulation. It's not obvious. It would be easier to just give up and say, no, this is not legal, I'm not able to do it. Okay, maybe it's not legal. I'm not even sure whether it's legal or not, but clearly it's accessible. This actual information is, you can get the solution to this query if only you reformulate it. Okay, this reformulation occurs all the time. So for example, the mediator has, one of the big things would be the mediator needs to have a schema. It needs to talk in terms of what attributes that it is exporting. Now those attributes may not be the ones that the sources have. So the schema mapping allows it to map the query into the language the sources understand. And there should be some rules kind of connecting this schema to this schema. Question, in semantic web standards, what standard will give you the ability to write those rules? What? What standard in the semantic web would allow you to write the rules, for example, connecting two schemas? OWL, exactly. Not RDF, but OWL. Right? So there is standard already if you were to write it. Okay. The question is, how do you, once you write this, then if there is a question on the mediator schema, they should be converted into the language that the other sources understand. And this would be a very interesting challenge that data integration systems would be interested in. Okay. But that would not sort of fall much here because they assume everything that you extracted is put in a single database under the table. And so you don't need to reformulate. You just have to deal with, in the unclean and inconsistent and possibly incomplete and possibly uncertain data. Now, the reality is that you have the problems of this as well as the problems of this. Because you can actually have an organization. Nowadays, actually, I think there are advertisements by major corporations saying they want to combine the data from their data sources into the data that's available on the social networks, into the data that's available on the web. Now, some of this data is at least structured. Some is fully unstructured. And so, in fact, when they extract the information from the social network, that could actually be probabilistically only true. So when they're doing that, then they essentially not only have normal databases and the challenges here, but they also have the challenges of probabilistic data. Okay. So these are kind of two extremes, but I won't even go into the middle right now. But pretty much you can read a paper on information integration and sort of figure out and sort of, if you're coming from here, you might be wondering why are they talking about query reformulation issues? And if you're coming from here, you would be wondering why are you wasting time with HMMs? Because the more interesting problems are reformulation. The reality is all of them are important. Okay. And the last slide that I want to do today, basically is just one slide again, the same guy, except now I'm going to give you 3 generic information integration architectures. Okay. 3 ways of doing this. And they have very different sort of trade-offs. Okay. And you can sort of guess which one would be more relevant to who. Okay. Now the simplest case is I have something working, search engines. Let me just do search engines, nothing more. Okay. So if in fact you have a database that you want Google to index, Google is happy to index it for you. Okay. One way to do it would be that you essentially kind of make the entire record into a page and do normal indexing. Okay, now, and so basically you're materializing the records. okay, into pages, and then you index them, and then you can include them in the search results. To some extent, a lot of that happens when Google is actually giving you answers. You know, for example, I don't know, I'm not quite sure right now whether they have API access to Amazon or not, but if you're looking for a book, they might be able to give you the direct pointer to the Amazon page that sells that book. Now, how does that happen? You know, one way that can happen, I can't be sure, I never will know what a particular private search engine is doing, but one way you can do it is if these dynamic pages are materialized, you know, they're just basically crawled and indexed the same way every other page is. Okay, it's like the cheapest way to now introduce. If you have structure, that's no problem. Just remove the structure and then we get to use it. Okay, this is, you know, probably like the lowest level idea, but it requires the least amount of work to set it up. There's nothing that you need to do, just, you know, make the page available. But then the integration is still done mostly in your head. You know, the relevant information hopefully might show up on the page, but then you need to combine pieces of information yourself. You can do a little better than that here if you do happen to know that, you know, basically the record that you get is an attribute 1, value 1, attribute 2, value 2, and so on. Okay, then you can increase, I mentioned this earlier, you can increase your inverted index such that it would not only remember where value 1 is occurring, but where value 1 is occurring right next to attribute 1. And so then you can ask some questions such as, give me all the records where Rav is the author. Okay, you still can't integrate information across sources, but you can at least give you more relevant information. You know, instead of saying, give me all the records that contain Rav somewhere, is different from give me all the records which have Rav as the author. And if you actually have converted structured data into materialized pages, you can then construct a inverted index that's bigger. I mentioned this in one of the classes, and you guys actually answered it to my surprise, that if you have structure and you want to index the information, your index will increase in size, because now the index has to capture the structure. That's one way, okay? That we understand. Another way is basically probably what you thought of first when I said integrate and a mediator. The idea here is that you have a user queries that are being sent to a mediator. Okay, the mediator then sort of sends queries to all the data sources on the web or wherever they are. Okay, and then to do this, it basically has to access the data from the data source by unwrapping it on demand, for example. So there may be, this data source probably has a form, so to ask a query to this data source, it has to automatically fill that form. Okay, and then when the data source gives the answers, it would be in some pseudo-English form, so it needs to then unwrap it. Then you will get a tuple here, then you may be able to join it with a tuple that comes from here, and then you can answer a query. Okay, does that make sense? Okay, now if you do this, so basically the interesting question then is this is sort of a broker. Okay, and the broker knows what sources are out there and which sources are likely to be relevant to which query, and then it sends this query that user gave to the relevant sources, gets the data, the answers from these sources, combines them, and gives the answers. Okay, now, so this is sort of the interesting thing here is the data sources are just live their own lives. You're not actually on demand. You go to the relevant data sources and get the information. Okay. Now the challenges here, of course, are first of all you need to design this mediator. Here you didn't have to design anything. Basically, it just becomes part of the normal search engine. Now this is data relevant to the normal search engine. Here now we have to design a mediator which does this, which should be able to, for example, have information about what sources are available to it. If it is an intra-corporate scenario, then you might know what sources are available and what are their actual forms, what are their query access forms. Okay, if it is web as a whole, then in some sense it has to go search for search for sources and understand what their capabilities are and keep that information along. And when a query comes, then you try to outsource it to the ones that you know. So it's really a broker model. And a broker is just as good as the customers that the broker, the sources that the broker can get your queries answered. Okay? And the challenges here, of course, are you have to design the mediator, you should be able to reformulate your query onto the sources in the right form. Okay? You need to be able to access the sources, you need to be able to collect the results. Okay, that's your,